video, I wanted to do a little matrix arithmetic. This is going to be very easy here. First of all, we've got R m by n. This is our symbolism for the set of all real matrices with m rows and n columns. Or another one is when I say a real matrix, I mean the entries are all real in the matrix. C m by n is the set of all matrices with m rows and n columns with complex entries. Complex numbers being those of the form a plus bi, where I squared is -1. Rm is the set of all matrices with m rows and 1 column with real entries. This is sometimes known as the set of all real m vectors or m column vectors. Okay? We'll expand upon the notion of vectors in a later video. We're only touching on it here as a matrix or an array of numbers for now. We can perform operations in each of these sets of matrices consisting of scalar multiplication, addition, and subtraction. Multiplication of matrices is a bit more complicated and will be discussed in a later video. A scalar is just another name for a number or numerical value, usually with units, but though we'll often not have that in this course, and is a name adopted from physics. Okay, we'll talk more about scalars later on as well, however. Each of these sets, Rm by n, Cm by n, and Rm, are called vector spaces, but that's something we'll have to expand on later too. Comes with a corresponding or underlying scalar field, that is, the set of numbers and associated operations from which the entries are taken. For example, Rm by n has corresponding field R. Okay, Cm by n has corresponding scalar field C, and Rm has corresponding scalar field R. You can always tell by what it looks like an exponent here with a base. The base is the scalar field. Let's talk about the operation of scalar multiplication. This is very simple here. Scalar multiplication involves multiplying a matrix or a vector by a scalar, that is, by a number. But the scalar must belong to the corresponding field to which the matrix or vector belongs. Vector spaces such as those shown above are closed under scalar multiplication. That is, the product of the scalar with the vector or a matrix will always lie in the same vector space as the original vector or matrix. Let's take some quick and easy examples here. Okay, if I had the following matrix 1, -2, 0, oops, let's come back here. We better make this permanent. Let's do this in blue anyways. Let's say I had this matrix A is 1, -2, 0, 5. We often use capital Latinate letters to designate matrices, as you probably know here. Okay, this is actually an element of R, 2 rows, 2 columns, as you see. All those entries are real numbers. I could multiply that by A and go 3A is 3 times, I'll use parentheses here, 1, -2, 0, 5. And what I would end up with is the matrix 3, -6, 0, 15, which is an element of the same vector space. In other words, it's also a real 2 by 2 matrix. And you see how I perform this operation. It's absolutely trivial. The scalar here, 3, simply multiplied on each of the entries in the matrix to yield the corresponding entry in the product. Let's do one with complex numbers here. Let's say I was to go B is the matrix 1, -2, 0, 2 minus I. Okay? Real numbers are also complex numbers. They simply have 0 imaginary part. But if I go like this, let's say I was to do this and then go 2 plus I times B, I would get the following matrix, 2 plus I times the 1, -2, 0, 2 minus I. And I would get 2 plus I, -4 minus 2I, 0, and then 5. Okay? For this last one, remember 2 plus I times 2 minus I. You simply FOIL these two complex numbers, treat it like a polynomial in I and FOIL. That'd be 4 minus 2i plus 2i minus I squared. And then you simply remember that I squared is negative 1. You combine like terms. And there you've got the 5, and that's where I got that value right there. Okay? Addition and subtraction. In order to add or subtract two matrices or vectors, it is necessary and sufficient that the two matrices must have the same dimensions and have the same underlying scalar field. In other words, they must come from the same vector space. The vector spaces are closed under addition and multiplication also. Addition and subtraction, I should say. Okay, I made a mistake on that. You should write subtraction. Okay, this is actually subtraction. Okay, let's try this though. It's going to be really easy. Let's say I had a couple real matrices. Let's say I go from 2 by 2 matrices again, and I was to add another 2 by 2 matrix, another 2 by 2 real matrix. I could do that. Now, you could add these because what? They have the same field, right? Underlying scalar field, which is the real numbers, and they have the same dimensions. They're both 2 by 2s. So you can add them, and how do you add them? Well, probably exactly what you think you do. You just add corresponding entries, and what you would end up with is another matrix of the same dimensions here, a 2 by 2 real matrix, 1, 3, negative 1, 12, reading across. If I tried something like this, though, if I went, say, this vector, 1, 2, which is just a column matrix for now, right? And I tried to add it to this matrix here, this does not exist. We'll just say D and E. There's no such thing. Because this is what? This is a 2 by 1. This is a 2 by 2. Their dimensions are different. There aren't even corresponding entries to add. So the answer here would be there is no such thing, or it does not exist. Okay, so it's pretty easy. Now let's talk about solutions to linear systems with infinitely many solutions. Suppose I had a system of linear equations, and I had used Gaussian elimination on it, and I had row reduced to the point where I've got this as my final matrix. And let's introduce some variables here and make it look augmented here. So I've got columns X, Y, and Z, U, and V here. You see from our terminology here, these are actually called basic variables, the X, Y, and Z, because the one here, the one here, the one here are all pivots, right? But these other ones, these are not pivots here, these other numbers here, and of course these are constants on the other side. But these other numbers here, negative 5, negative 2, negative 1, 4, 8, 9, these are not pivots here. So these, the U and V, are called free variables here. And what we're going to do is write our solution to X, Y, and Z in terms of those free variables U and V. You take the first row, and what would it be saying? It would be saying 1x, in other words, x plus 0y plus 0z, minus 5u plus 4v is equal to 6. The next one would be saying y minus 2u plus 8v is 7. And the last z minus u plus 9v is equal to 3. Okay, now if we were to solve for x, y, and z, the basic variables in terms of these here, we would do this. We would say x is 6 plus 5u minus 4v. Y equals 7 plus 2u minus 8v. And z equals 3 plus u minus 9v. And then I want my solution set to be x, y, z, u, and v. Now u and v are free variables, so that's going to be 0 plus u plus no v's, okay, to just make everything look the same. No u's plus 1 v, so I'll just write v there. Now if I was to write this as a vector, right? Just a column matrix for my answer, x, y, z, u, v. Then what I could do from scalar multiplication and scalar addition and everything, that's part of the reason I'm emphasizing this in a separate video. It would be this vector plus this vector times u. You could put the u in front or behind, whichever you want to do here, it doesn't really matter. Plus -4, -8, -9, 0, 1 times v. Okay, so this would be our answer. Okay, so there you go. All right. One last set of operations here that we would like to take a look at here is the transpose and conjugate transpose of a matrix. Okay, each one is under a certain context here. You take transposes of real matrices and conjugate transposes of complex matrices. Okay, these are quite easy, however. Okay, you can read here the transpose of the matrix A in R m by n is the matrix A superscript T, that's read A transpose, in R n by m. Notice how the dimensions have switched. This is because it's obtained by switching or interchanging the rows and columns of the matrix. Thus, an m by n real matrix becomes an m by m real matrix. So this is going to be really easy. So if I had this, if I said A was 1, 2, 3, 4, 5, 6, and that would imply that A transpose, so superscript T, is going to be the first column becomes the first row, or the first row becomes the first column. Let's do it that way. The first row is 1, 2, 3. That becomes the first column of the transpose. The second row is 4, 5, 6. That becomes 4, 5, 6 is a second column. And there it is. Okay? You can see how the dimensions have been switched. This is a 2 by 3. This, however, is a 3 by 2, both real matrices. If you remember, let's talk about the conjugate of a complex number. If you've got a complex number a plus bi, the conjugate of the complex number is just obtained by changing the sign on the imaginary part, or signature on the imaginary part. Okay, so for example, and there's also a notation here. If I go 2 plus 3i and I put a bar across the top, if you remember from college algebra or wherever, you change the sign on the imaginary part. This is read the conjugate of 2 plus 3i, so that would be 2 minus 3i, and that's all there is to it. If I take the conjugate of that in turn, I get back to my original, don't I? Okay, now the conjugate transpose of a matrix B, say, in C m by n is the matrix B subscript star, or B star. This is conjugate transpose of B. This is the matrix in C n by n, attained by taking its transpose, that is, by interchanging the rows and columns of B, and additionally taking the complex conjugate of the entries. So let's go ahead and take an example here. Suppose I had B was this matrix, 1 plus I, 5, and 6 plus 2i. Okay, if I was to take its conjugate transpose here, so I'll go B star, it's going to be this. I've got to make the first row the first column, so it becomes 1 plus I, but don't forget you also have to what? Take the conjugate here. So it becomes, reading up and down, 1 minus I minus I. The conjugate of 5 is just 5, because you think of 5 as 5 plus 0i, plus or minus 0i, it's not going to change. And then what? 6 minus 2i. And that would be the conjugate transpose. So this is pretty easy stuff here. So we're just doing this for the sake of completeness.